Today I'm going to talk about practical approach to automate the discovery and eradication of open source software vulnerabilities at scale. So I gave this talk at Black Hat this year, and Travis, who is not here today, one of the OWASP members, chapter leaders, he suggested I give this talk at OWASP, so I can share this knowledge with you all. This talk originally was 50 minutes. And I tried to cut it down to 30 minutes. So I removed almost half of the slides. But if you are interested in the full presentation, full slides, full video, they're going to be published on YouTube with Black Hats. So let's get started. So we're going to talk about today, we're going to talk about the problem of open source security. We're going to talk about some of the attacks that we see in open source dependencies. We want to touch base on, talk about in details about the approach. So our approach means the solution that we came up at Netflix, and then some future work. Before I start, let me first introduce myself. My name is Aladdin, and I am on the application security team at Netflix. Our team charter is to help engineers at Netflix improve the security of their software. So I think everyone in this room agrees on the actual value of open source, right? I think we use it in all the projects, in all applications. And this adoption has been accelerating over the last 10 years or so. This is actually a really good trend for the industry. It makes us move faster. We can develop more tools, and also gives us more flexibility and agility. But we all share the same frustration when it comes to fixing and finding vulnerabilities in open source. So let me tell you this. So you come in the office on Monday morning, you're very excited, you want to do the actual productive work, when you suddenly saw this. A serious remote code execution vulnerability was found in one of the popular open source packages. And what happens to you? You're freaking out. Now, you have to get into it. But before that, you need to answer a lot of questions. So you start the process of identifying the answer for all these questions. And you come back on Tuesday, you continue going through all these questions, and you're missing lunch. And now your whole week is gone. According to a report from Sneak, the adoption of the number of these vulnerabilities in open source has been accelerating. So there is also no sign of it slowing down. And so the thing that you were doing on Monday, given this chart, you probably have to do a lot of these, probably 6 of these every week. And I guess nobody wants to do that. So this is the actual real motivation for our approach, or the solution that we need to come up with. I really don't want to waste my week just trying to identify every single dependency, every single vulnerability. I want a solution that will be able to do all of these things for me. I can just sit at my laptop, do the actual productive work, and not worry about this. But now let's ask a question. Why is open source really a problem? Like, why we actually even talk about it? So if you think about the open source problem in general, there are some unique challenges. Most developers, first of all, have limited ability to evaluate the problems or the security problems in open source. How many of you have worked with developers where like a developer like, hey, I found this vulnerability in this open source package, and like, please, we want to fix it. Like, what is the chance that this could happen? It's very low, right? So imagine you're doing this at scale, and there are thousands and thousands of packages and thousands dependencies. The sheer volume of these vulnerabilities is huge. As we saw on the chart, these vulnerabilities is going to increase. I mean, the number of vulnerabilities, the number of packages exist today is huge. And the number of vulnerabilities comes with these packages is going to also increase. And this is just talking about the actual packages. And then talking about the transit dependency is another problem. What is transit dependencies? So imagine you have a package called A, and that package is pulling a direct dependency called B. B is also relying on another package called C. This C called indirect dependency or transitive dependencies. Now this chain can go bigger and bigger. So C can also have D, and B also can have D. So in this case, C is relying on D and B relying on D. In those cases, those are also called indirect dependencies. Does anyone know what is this? This is not a jellyfish. Any guesses? Huh? Yes. So this is what we call Python dependency graph. So it's basically a collection of all the packages in Python, and they basically collected all of them and then parsed all of them and created the dependency graph. This is another chart that shows the Maven dependency graph. It's huge. So imagine you have to go and find vulnerabilities in this huge dependency graph. It's a very complex problem, and this is cause for a developer what we call dependency hell, where you, as a developer, have to go and find a way to resolve all the conflicts between dependencies. And it creates also a really big problem for us as security engineers, where we have to not just find, but like remediate those vulnerabilities in open source packages. So these are some of the examples where like we're talking about vulnerabilities. But if you think about it, there are things that does not really necessarily require a vulnerability to exist in a code. There is what we call the malicious codes or malicious packages. So the code is actually the malicious code comes with the library and does not require any additional attacker. The attacker actually is in the package or is in the library. How does that actually happen? So most attackers prefer what we call the covert channel attacks, such as phishing, right? One of the most common effective covert channel attacks is injecting code or malicious code into packages. This is what we call supply chain attacks. And the attacker doesn't necessarily target the actual organization, but they target the trusted vendor by the organization itself, where they know that this particular vendor is being used in that organization. So in this example, for the NPM package event stream was backdoored. So how is actually malicious packages introduced into an ecosystem? Well, there are different ways. Maybe some of you are aware of these attacks, but I'm just going to talk about them in case you don't. So the first one is called typo squatting. And typo squatting is simple. Instead of typing, for example, npm install express, you type in express. Now, if that package wasn't reserved by a legitimate user, the attacker could actually go and create all these typos packages and put malicious code inside them. So if that package contains malicious code, then it's actually installed in your server or in your laptop. So that's what we call typo squatting. Has this happened? Yes, for NPM and Python. So in the Python example, the package name Colroma was typo squatting colromo.io. The other type of attacks is called package masking. So internal package can have the same name as an external one. So if you are, as a developer, can create a package called foo, but you can ignore the fact that there is an external package called foo. So if an attacker would guess the same name, then they can create foo with a higher version, like 9.9, for example. Well, like they expect that high version higher than the version that you're actually using in your code. And what happened is, the reason this works is because the package that has the highest semantic version will win. So when you go and build your code, the actual foo, external foo, will override the internal one. It's not actually an override process. It's the highest version will win. So the external one will be picked up. And that's how most, I would say, attackers would target a large-scale compromise. They know the actual package name, and they guess it, and then they publish the same name. So this is how it works with example. So the developer commits code. That code is called company.lib.x, version 1.2. The package gets published to the internal repository. Now let's assume there is an attacker. The attacker will guess the same name, which is company.lib.x. And then they publish a newer version with the backdoor in it. And they publish to the external repository. The next time developer builds the code, because there is a mirroring process happens, the external one will be picked up. The other one is called ownership transfer. And ownership transfer happens because of retired developer. Maybe retired developer is extreme here. But someone who actually doesn't have time to maintain a specific library or a package gives the ownership to someone else. Now, if the person who took the ownership is malicious or untrusted, then they can actually backdoor that package. The fact that this package is already installed on thousands, maybe, and hundreds and thousands of machines or servers, the attacker will have a leverage over that. So they can just publish a newer version, and then the next time those servers will pick up the new version. The other attack is called dangling references. So this is something I observed over a couple of packages I saw. So what happened is basically the developer builds a library, and they add things like URLs or S3 buckets. And what happened is that's called a resource. So like either a URL or an S3 bucket. So the developer forgets about it, and like time flies, and then the domain or the S3 bucket has been deallocated or has been removed. But they forget to remove the actual resource in the package. So what attackers will do, they look at these things, and then they'll go and reserve the domain. And so for this specific domain, for example, this is an example. There's actually a real one where a domain wasn't reserved, so it was taken over by the attacker. And then because this URL is pulling actual code, the attacker had the leverage by attaching their own specific script into the URL, and then the next time the package runs, that script from the attacker will get executed on the local machine. It's pretty powerful. I have looked at probably 100K packages, but there are like millions of packages, so you probably will see more of these. OK, so if all of these things don't work for the attacker, what they could do is they can do dependency infection. And dependency infection relies on a couple of things. So the attacker will look at a couple of things before they decide to do dependency infection. So they look at the popularity and reputation of the package. So how many downloads it has, how many people are using this package, how many people are actually trusting this package. They look at the number of direct and transit dependencies. And they also look at how the classes are being used in the application. Does anyone notice anything about this image other than it has hundreds of dependencies? Any guesses? Look at how many maintainers. So this package has a lot of maintainers. And what the attackers do is they look at these things and they compromise maintainer accounts. So they find like a common, very famous package. And what they do is they look at the actual maintainers and then they'll try to compromise them. Most of the, if you look at the history of all the compromises, it's because of actual compromise of maintainers. NPM does not enforce two-factor authentication. They have it as an option, and they actually recommend maintainers to use two-factor authentication. So the way it works is they send obfuscated commits to maintainers sometimes, and the maintainer doesn't have a time to look at the code itself, and they just happily accept it. And sometimes they compromise the actual laptops of maintainers. They compromise CI/CD of maintainers. How many people have seen Jenkins instances on the internet? I have seen like maybe 3. You saw one? So those Jenkins instances typically are sitting on the internet, no authentication, and someone could actually compromise them. And also internal package version override, the one we were talking about. So how do you actually protect yourself from these things? I guess the first thing is you can use scope registries. This is to avoid the shadowing of packages. So it defines a scope of what is actually internal, what is external. You can use also package signing. And package signing is very important. You can use dependency locking, although some people would argue that dependency locking would not give you the latest and greatest because you're actually pinning to a specific version. You can also harden your CI/CD infrastructure if you are a maintainer. And you can use proxy to force internal packages to always take precedence. Some companies will run these internal proxies, so they actually block the external ones. And for maintainers to use two-factor authentication. Now, let's talk about the actual problem and how did we actually solve it at Netflix, considering that we are focusing on both the supply chain attacks and the actual vulnerabilities in packages. So our approach consists of 3 stages: discovery, triage, and remediation. I think everyone will think in this room the same exact way that if you want to solve this problem, you would think about those stages. But let's talk in details about like each of these stages. So the discovery stage is basically we want first to be able to find or know about the vulnerabilities that it may affect our systems. So this is where we wanted to get some feed or some information about the known vulnerabilities externally. So you could do many things, right? You can create your own crawler. So you start crawling for NVD database. You get all the data. You don't necessarily get everything, but at least you get some of it. And then you look at different sources. You look at NPM, you look at Debian, you look at all these sources, and you start basically collecting and accumulating all the data. You can also use OSS vulnerability intel sources, and you can use commercial OSS feed. Now, you can fetch this. You can grab everything and build the whole service. But this adds additional complexity, and it's a solved problem. Like, I'm not really solving anything new here. So I decided to actually purchase a premium feed. And that premium feed will, on the 24 hours, give me all the known vulnerabilities in all open source packages, and make sure that that feed gets updates. It could be that you make a different decision. You decide to build the crawler yourself. You can do this for sure. But for me, I think it's more of there is actually very cheap services that can give me the information that I needed without worrying about building the whole service from scratch. And so I can focus on the other things. Now, the feed, the minimum things that you need to have in the feed so you can do some automation is the vulnerability description. If there is an exploit in the wild, there's other metadata. but those are the main things that you probably need to have in the feed. If there's actually a flag that will tell you this is a malicious code. If there's a specific package, like what is the malicious code, what is the malicious version of the package that gets impacted. And also, if they can tell you about the package vulnerable methods. So you can do some tracing. So the next step is you have the feed now. You have the JSON data. You want to actually map all this data to who from the services that you're using or the services that you're running using those particular versions of the vulnerable libraries. So how do we do that? You want to build a dependency graph, what we call dependency graph. And the way you do that is you parse the manifest file. Now, most companies will go and try to parse the manifest files in the local repository. The problem with this is with the semantic ranges, you won't be able to tell like what is the actual version that is pushed to production. So for this particular version of load dash, because they are not specifying the actual version, then it's going to basically install anything on 4.x.x. So you won't be able to tell. So how did we solve this problem? So we built a system called Astrid. And Astrid, the main goal of Astrid is if you are a developer and you want to know the impact of the libraries that you're building, then you can query Astrid, and Astrid will tell you who actually is consuming that specific library and where. So, but how does it actually know about like where is the actual package being installed, and how does it actually know about the versions? So the way it works is it looks at three things. The first one is published artifacts indexing. So it performs indexing operation on the artifacts. It does this the same thing on the deployable module and the AMI manifests. So I'll give you an example. Let's say that you have a jar file, and that jar file is used in your application. What Astrid will do is it goes and grabs the jar file, and it grabs all the metadata. And it does what we call recursive build. So it goes and builds the whole dependency graph for that specific jar and stores this information in a database. It does the same thing with the deployable module indexing. It goes into all the Debian. It scans all the jars and finds the hashes of the things that has been already indexed. If it's not found, we'll do the same process again and store all the data. We do the same thing with the AMIs. We scan the file list for all the Debians, and then we do the same process as before. So now we have a full database indexing all the artifacts with the actual instances that where this artifact is being installed. This is because all the deployable modules goes through a bake process. So when we do baking, we know exactly that we have indexed everything in this particular AMI. So I can ask Astrid and say, hey, Astrid, can you give me who's using this particular package and this particular version? So Astrid will happily come back and say, OK, here is the number of instances are using this package, and those are the names or the IDs or the container IDs. Cool. So now I can query Astrid, giving any package name and package version. I know exactly where that package is installed, which servers are using this package, or which Docker containers. So I have a map of all this information. Now think about this process. There will be thousands and thousands of results, right? Given a specific package, the results will be huge, specifically when we're talking about like famous packages. So when we looked at the list, we had to basically look and decide to do like some triaging process. So what is triaging? So I think the oldest model of remediating every single high or critical vuln might not really work with open source. This is because, as I mentioned, the sheer volume of these vulnerabilities. And so And also, if you think about it, not all the critical and high vulnerabilities would pose a security risk, right? If you are running a package that CVSS score 9.5 or 9.6, there are so many other environmental factors that would determine the risk of that vulnerability. So we decided that it's better to have some sort of formula or a defined strategy that we can use to conclude the risk. So the first thing that we can't ignore is the CVSS score, and then the application risk, and if the vulnerable method is ever executed. And this is very crucial. We also look at if the active exploit in the wild, and if the application itself is internet-facing. You might be asking, how would you know if the application is internet-facing? I guess this is a solvable problem. You can look at all the, you can run some scans from outside. You can do Nmap. You will have some way to tell like if a specific application is actually internet-facing. So you have this information now, and you can generate some conclusions about specific vulnerability. So you can say, OK, for this particular vulnerability, this application is internet-facing, and there's an active exploit in the wild. This specific application is actually using the vulnerable method, and the application risk is high. So the application risk is high. You can categorize that as well. For example, if you have a payment system, the risk of that system is higher than something else, and depending on your environment. So the conclusion here is that this vulnerability is actually risky, and we have to take an immediate action. So we do specific actions based on this. This is another example where we think the risk is insignificant, and so we decide not necessarily we have to remediate this issue. This is because there's no active exploit in the wild, and the vulnerable method never executed in the application. This is another example where we think it's moderate. So the vulnerable method is actually executed, and there's an active exploit, but the application is never internet-facing. So this thing, moderate, means we don't have to take an immediate action and solve it right now. OK, so now we have at least a trimmed-down version of all the vulnerabilities. So let's say that we have concluded that from 100 vulnerabilities, we will just want to fix or we want to resolve 4 or 5. But how do we actually do the remediation process? So there are minimum things that you would need to have in order for you to do automated remediation. The first thing you need to do is, what is the actual minimum version that you need to update that will fix the issue? The reason I'm saying minimum version is because you want to avoid breaking changes. If you want to actually upgrade to a major version, then you may actually break the application. You want to have knowledge about the first order dependencies. I'm going to talk about this. And then you want to identify all the blockers. So what is the minimum version dependency, minimum version update? So let's say that you have an application. The application is using a package called foo. And this foo has 2 different CVEs. The first one is affecting 2.x to 2.4.0. The second one is affecting 2.x before 2.4.9. Now the conclusion, because you look at it, it's easy. You can say like, OK, the fix for these things is 2 versions, but because I want to fix both of them, I just want to ask the developers to update to 2.4.9. But how do you actually do this? So this technique works for us. So what you do is you first find all the versions from center repository. So for a particular package name, you pull all the versions from the repository. And then you identify the vulnerable versions. Because you already have the vulnerable versions in the feed, you exclude all these vulnerable versions from the full list. And now you have only the good list. So what you conclude is the minimum version and the latest version. The reason you want the latest version is because sometimes developers need to know what is the latest version so they can just upgrade to the latest version. But you still need the minimum version to avoid breaking changes. OK. Now let's talk about the first order dependency. So in order for you to be able to fix, I think the core of the problem is just in this like few slides. That's most of the issues that we were like struggling how to solve. So think about that. If you have an application, that application is using a particular package called A, and this package is called version is 1.0. So this package relies on other versions as well, other packages, C and B. And C also relies on the E and D. Now, let's assume that this package F is vulnerable. So this particular version is actually vulnerable. So in this particular case, we know that F is vulnerable and H also is vulnerable. Now, for the application to upgrade, they will need to fix the issues in E and B. So B and E are blockers. The reason they are blockers is because they are the only one that can take action on F. Meaning E can say, OK, I can upgrade F to 2.1. And B can say the same thing. I can upgrade H to 4.1. But how do you actually find this first order dependencies? So the way we did it is we preserve all the metadata of all the packages for in which were they actually built. So because if you remember the indexing process where we preserve all the data, we know exactly where the package has been built. So we know the Git repository of the owner. And so what we do next is we scan everything. So we scan all the packages. And in every module, in every deployment, we look at subgraphs. So in this particular case, we look at all the subgraphs that determines or finds a specific vulnerability. So this circles in red are the vulnerable packages. And we list down all these subgraphs. And in every subgraph, we find the immediate consumer of the package, the vulnerable package. In this case, K is immediate consumer is A, and etc. Now, what we do next is we check, is the immediate consumer the same library owner? So we ask the question, is foo and A the same library owner? If yes, then foo actually can take action on A. And the action that needs to be taken on A is to upgrade K to the newer version that does not have the vulnerability. And what we do next is we keep checking to see if not, so meaning if the other packages that are consuming K are still blocked by the action that foo needs to take. Once foo upgrades A, which upgrades K to the none or free vulnerable version, then in this particular case, all the other projects can upgrade. This is an actual real image of shows all the transitive dependencies. So the primary blockers in this case are the pink dots. This is a real campaign that we ran for a particular package, vulnerable package. And so the pink dots, once they upgrade, then all the green, which are the affected services, can actually upgrade to the latest version. So what do we have so far? We have the list of all impacted services based on a particular vulnerability. We have a full triage list of all the services based on the criticality. And we have also the list of actionable and the data about the remediation versions. So we have all this data now. We can conclude things such as remediation strategy request. So we can say, OK, there are things that would require immediate resolution, and there are things that can wait. So for the things that requires immediate resolution, we can do things like resolution strategies. And resolution strategy, think about it that you're actually forcing a specific version. So if you know that there is an immediate action needs to be taken for a specific vulnerability, like struts, for example, then you can force that version to say, OK, substitute this module with this module version. The other thing you can do is also you can issue automated pull requests. So what we did is basically we tried to create pull requests where it's actually using the minimum version. We issue the pull request to the developer saying, hey, can you upgrade to the latest version or the minimum version? This is actual image of the application that UI. This is just a UI. The whole system is run automatically, so it runs as a cron job in the night. But this is just to show you like what we actually could do manually if we wanted to. Now, the other thing I want to talk about quickly, I think I'm over time, but there is a concept what we call campaigns. And since we know the actionable things to be done, because we identified the actionable from the graph, we can create what we call campaigns. And the goal of campaigns is to propagate changes across all the environment really quickly and show actionable information to developers. So we can say that, for example, this particular version of the library is deprecated. So we can go and say, OK, this particular version, like structs or something like really critical, blacklist it, which means it's going to be blocked when the developer actually build their systems. This is to avoid the potential problem that the next build will have the vulnerable version. This is actually showing a graph of real vulnerability where you can see the decrease over time. So you as a security engineer can sit on your desk and just watch this happening. You can do follow-ups if you want, but this will be done automatically. For the things that can wait, we have something called QCC, or quarterly change cycles. And what we do is basically, for Netflix, it's very important not to prevent developers to do the things they want. So what we do is every 3 months, we try to decrease the cognitive loads on developers. So we issue campaigns. And those campaigns are similar to the Blacklist campaigns. The difference is they are deprecation campaigns. So they don't necessarily black the build. So we give the developers the flexibility on when they actually want to fix it. But then we're going to see also the decrease over time of this particular vulnerability. What work still needed? I think the most important thing is the vulnerable method use detection, and that's something we're working on. Given that we actually know the name of the vulnerability, can we tell if the vulnerable method is actually ever executed in the lifetime of the application? We want to have better remediation, means we want to issue Slack messages to developers, given that we do full testing everything for the vulnerability fixes. Then the developers just need to go and accept the pull request and merge it. And some organization metrics, I think this is very important for managers where as a manager, I want to know how successful the system is and what can we do to make it better. I think final thoughts, you can't just ignore the problem of third-party dependencies. It's very important. It's part of any other security problems that you may have in your organization. You want to actually empower developers to use third-party dependencies, but you can't just block them on every single vulnerability that you're seeing. So you want to have concrete decisions based on the risk. And I think building automation is kind of hard, but will reduce the cost and operational cost, reduce the risk and operational cost. Again, this talk, I gave it at Black Hat. It has so many other details about like the process that we're taking for the remediation and the triage. So yeah, once it's published, please feel free to watch it. It's the same title. And yeah, that's my talk. Thank you very much.